Hi, thank you for watching this video. I'm Wanrong Zhang. I'm a PhD student at Georgia Tech. Today I'll be talking about attribute privacy, framework, and mechanisms. This is a joint work with my advisor, Rachel Cummings, and Olia Orimenko, who is at the University of Melbourne. Attribute privacy protects the global properties of sensitive attributes in a dataset from leaking during analysis. For those of you who are familiar with differential privacy, we're used to thinking about privacy at the individual level, corresponding to rows of a database. And we ask questions of the form: where can an adversary learn about Alice data based on an analysis of this dataset? In this work, we instead consider privacy of the attributes or columns of a database. That is, we take the view of a database owner who wishes to publish aggregate statistics about her database, and must also protect privacy of the aggregate information in certain sensitive columns. In this example, the owner may wish to publish average SAT score of its students, and let's assume that's non-sensitive information. However, we know that SAT scores are correlated with sensitive attributes, such as race, gender, and socioeconomic status. So even though SAT score column is not sensitive, privacy protection is still needed to prevent leakage of other sensitive attributes. There are many other use cases for attribute privacy. For example, hospitals want to share the number of COVID cases with federal health agencies, but want to protect mortality rate that may affect future funding opportunities. Companies want to share client data, for example, standardization, but want to protect proprietary information. Researchers want to provide data for reproducibility in peer review process, but don't want other researchers to perform new analysis on the data. In general, attribute privacy is to share aggregate statistics of a dataset, but want to protect other aggregate properties that might be correlated with the shared information. Since it's a short talk, we will be focusing on the framework and definitions of attribute privacy. We also propose a few mechanisms, and we will just briefly introduce them at the end. Our formal definition of attribute privacy are based on the pufferfish privacy framework. Pufferfish privacy generalizes differential privacy in two ways. It allows the analyst to specify distributional knowledge about where the data came from, and the domain knowledge about where what should be kept private. It can also accommodate correlated data, but the correlation was across the rows. The pufferfish framework has three components: a set of secret S. Then there's a set of possible facts about the database we wish to hide. A set of discriminative pairs. Then there's pairs of secrets we wish to be indistinguishable. And a class of data distribution data. Then capture conservative assumptions about the underlying distribution, then generates the database. Formally, we say a mechanism is epsilon delta pufferfish private in a framework SQ theta if for all possible data distribution in this class, and for all secret pairs with non-zero probabilities, and for all possible subset of outcomes. The probability of the outcomes conditioned on the secret pairs should be close in this multiplicative sense, with high probability 1 minus data. We first introduce a data model for attribute privacy. So a dataset X contains n records with m attributes, and we can view this as an n by m matrix. And remember, DP want to protect privacy of the rows, but we want to protect the privacy of the columns. And xi is the ith column, then corresponding to the ith attribute, and xij is the jth record. We assume each record is sampled ID from an unknown distribution, where the attribute within a record may be correlated. And C is the indices of the sensitive attribute. And the data owner want to evaluate a function f, and we want to release f of x while protecting other information about the sensitive attributes. We introduce two notions of attribute privacy. Before we make those definitions formal, we'll start by distinguishing them. The first one is dataset attribute privacy, which protects the attribute of a particular dataset. And the property of the attribute could be were there more Caucasians or Asians present in this dataset. And we model this property as a function ji of a certain column xi. Our second privacy notion is distributional attribute privacy, which protects the parameters of the underlying distribution from which the dataset was sampled. For example, the property is, were there more Caucasians or Asians present in this population than was sampled to create this dataset? And we model this parameter as a parameter phi I, then govern the distribution of the ith attribute. And you may wonder, wait, aren't they the same? They're almost the same in the above case, since j of xi is just an estimate of phi I. But the distinction is important when guaranteeing privacy for unlikely realizations of the dataset, such as the max and the mean, or when n is small and the g of xi is a poor estimate. And here is our formal notion of dataset attribute privacy. Okay, it might be the most dense slides you've ever seen, but I promise all the details are important. Let's start with a data model. So xij is a data record sampled from unknown distribution D, and our data set contains n records, then the sampled ID from this distribution. In other words, our data set contains n ID samples, then were drawn from a drawn distribution of the attributes. And C is the indices of sensitive attribute, and Ji of xi models a property, and its codomain is ui. We formalize our attribute privacy definition using the pufferfish framework by specifying the three components. The S contains all the secrets, and the secret is the event, then the JIXI takes value in a certain set. And this S includes all secrets for all protect attributes. And it includes all subsets or only certain events. And the Q is a set of secret pairs. It includes all pairs of disjoint event on the same sensitive attribute. And the F and the theta is a set of possible distributions. The pufferfish framework considers distributions over the entire dataset X, but we consider distributions over records. We resolve this by defining theta to be the collection of distributions over datasets, then induced by the allowable ID distributions over records. And this slide is our notion for distributional attribute privacy. Okay, this slide is even worse than the previous one, but again, they're all important. So start with data model again. We assume each data record is sampled from an unknown distribution, then described by parameters phi I, where phi parameterizes the marginal distribution of xij conditioned on the value of all other phi k fixed. And this phi I are drawn from a joint distribution P. So although it seems natural for phi I to define the marginal distribution of the ith attribute, this wouldn't capture the correlation across attributes that we wish to study. Instead, phi I defines a conditional marginal distribution of the ith attribute, given all other phi k fixed, which does capture such correlation. This also allows the distribution over dataset to be fully specified given phi and the size of the dataset n. And then our instantiation of the pufferfish framework is very similar to the previous definition, with this attribute-specific random variable phi I taking place of the attribute-specific function gi. Given the notion of attribute privacy, we also have 3 mechanisms to achieve that. The details are present in our paper, which you can find it online. We will just briefly introduce them here. We propose an attribute private Gaussian mechanism, and it satisfies epsilon delta dataset attribute privacy when the query answer conditioned on the aggregate secrets is Gaussian. We also have attribute private Markov quilt mechanism. It satisfies epsilon zero distributional attribute privacy when the attribute follow a Bayesian network. We have a fully general mechanism, the attribute private Wasserstein mechanism. Since it was proposed to satisfy the general pufferfish framework, it automatically satisfies both attribute privacy definitions. But this is computationally inefficient. The above 2 mechanisms are computationally efficient, but they require some assumptions. The open problem for us is how to design the computationally efficient mechanisms without assumptions. The main takeaway is we introduce dataset attribute privacy and distributional attribute privacy to protect privacy of attributes rather than the privacy of individuals. And we show that the pufferfish framework can be instantiated to accommodate correlations across columns, which is needed for attribute privacy. We propose 3 mechanisms for satisfying attribute privacy. As we mentioned in the beginning of this talk, attribute privacy has many applications. The future work includes applying and adapting these tools to relevant applications for domain experts. Thank you.